Very happy to join this BioLadies meetup. I think I'm the only bio lad. But anyway, I think very happy to talk about biopolymer materials. And I just talk through using this a few minutes to talk through just a few studies, some observations about the materials, biopolymer materials with their unexpected properties. So I think the first I will talk about my research. Briefly, my research is about in three aspects: fundamental material science, and also polymer engineering, how to make biopolymers into materials. Not only biopolymers, I'm also working on some other polymers, but biopolymers is the thing that I have been focusing on. And also I'm looking at developing different materials out of biopolymers, because normally we have to look at combining different ingredients to develop the materials formulation in order to achieve the best properties. So these are material science and engineering, especially polymer material science and engineering is what I've been working on. So my research is mainly about natural polymers. So natural polymers could be cellulose. Just now we talked about hemp, and the main ingredients in those plants are cellulose. We also have a starch, and also have a chitin or chitosan. Actually, they are very similar things. A little bit difference in chemical structure. They are from and also alginate from seaweed, and also fibrin, silk fibrin. And also we of course we can look at other protein sources that can also be made into materials. So these are the things that I'm looking at. So very quickly, I think starting from a few years ago, I'm looking at using ion liquid to process biopolymers. And I think a lot of people are doing using ion liquid for cellulose. But here in this case, I'm looking at using that for starch as another biopolymer. And using that, I can find that I can use ion liquid, especially with a certain amount of water there. I can convert that into a gel, and then in this way we can do materials. And I think this is very important because all these natural polymers, including hemp and other things, I think we have to dissolve that, we have to generate that in order to make materials. I'm also looking at another one is using this aqueous metal chloride salts to do the same thing. This is cheaper. Ion liquid is more expensive, but this is cheaper. I also find that a certain ratio of these salts solutions will be able to treat these biopolymers. And in this way, we could get materials. If we regenerate materials from these dissolved biopolymers, we can get some particles which can potentially be used for some pharmaceutical applications. And these are some characterizations showing they are mostly amorphous, which is very useful for some electrical conductivity, electrical applications. And also this just shows that these solvents are not causing any chemical effect. So in that way, with these solvents, we will be able to make starch into a film, into a strain-sensitive film. So these are just the results showing its strain sensitivity. And also we can use this strain-sensitive hydrogel be able to detect like some human behavior, pulse or finger bending, stapling, etc. So this just shows these materials can be used as these for these electronic applications. Also, we can make batteries out of that. We can develop formulations, adding some metal powder into that. We can create batteries, and these batteries will be able to also strain sensitive, because you press that, you can see the change of the light brightness. And also in this way, we can detect its responsiveness to stress and strain, and it can be used repeatedly. So this is the battery. And further, we could be able to develop a self-powered sensor by combining these so-called battery with some carbon cloth. So they are fully flexible, and they can also be very sensitively reflect to change its current, have the current change to be able to change with the different stresses. So this also shows its responsiveness, sensitivity, and it can be used repeatedly. And this curve can still reflect that change. And also, again, we can use this self-powered sensor to be able to detect human behaviors. So these are just quickly go through these development. The other thing that I'm looking at is just to prepare materials, because sometimes we need to have the best material properties. One thing may not do all the job. We have to combine different things together. Here, in this case, I just show you that I combined chitosan with silk peptide. So this is something, a hydrogenized form of silk protein. So easier to process. And we combine them. We use this way, hot press, mixing and hot press to create a film. And we can see that it has very good mechanical properties. So this is just because of the interaction between these different components there. And also, this case just shows that we use chitosan, carboxymethyl cellulose, and clay system. We use a very similar protocol as shown in the previous slide, and we can get different formulations. But one interesting thing that we have observed is that these materials, when we combine two things together, create the material, we will be able to get better hydrogenetic stability. And this stability is better than the materials prepared by only chitosan or only carboxymethyl cellulose. So that means there are interactions between them. So in this figure, on the left image, you can see that only chitosan will be dramatically swollen and become very fragile if you put into water. But if we have two things there, they can be more stable there. So this just shows the importance for the to develop the materials formulation. And these are just to combine two biopolymer together, we can get very different effect. So here we have dimensional change and weight change just to reflect these changes. But the interesting thing is that even though they are more stable in water, but I would like to say that carboxymethyl cellulose actually is more hydrophilic, and we have this one. It has a lower contact angle, which means higher surface hydrophilicity. So even though the surface hydrophilicity is higher, it is more stable in water. This is something very interesting, even though a bit counterintuitive. But I mean, we can consider the materials, the internal structure interactions between the polymer chains, and also we can consider the surface chemistry to have a different surface hydrophilicity or hydrophobicity of the material. These are all the things we can consider for the materials design. So this slide just shows the interaction between the two biopolymers, and I consider that because they are actually they are not neutral. They are positively charged. Chitosan is positively charged, and carboxymethyl cellulose is negatively charged. So they have ionic interaction. We call that polyelectrolyte complexation between these two types of polymers, and these just stabilized the materials and to give it better properties. So very quickly, just show some examples in my research, but I would like to say that what I have been doing is polymer science and engineering, and I have worked on the dissolution gelation process of these biopolymers. They are very important to be for use. We have to process that cost effectively, and I'm looking at different biopolymer materials, films, hydrogels, and other forms as well. Actually, I'm looking at and using different manufacturing processes like the mixing or hot press I showed in the slides, but also 3D printing or something to create the desired materials forms. And also composites. I have been working on combining different ingredients together, not only different biopolymers, but also I'm looking at using different nanomaterials incorporated to give the best properties or desired functionality. And functionality, we can have conductivity or stimuli responsiveness and any other things, and we can consider. So this is all about materials development. Yeah, and that's my talk. Thank you very much.